Good afternoon. Today, we're going to be looking into equations once again, and we've been looking at all types like categories, including conditional, contradiction, as well as identity, and we've also looked at equations of varying degrees, including linear and quadratic. And for what we'll be looking into for starters today, will be radical equations. And in the case of radical equations, now we've looked at radicals in the sense of simplifying radicals, like in the case of square roots, especially those square roots of numbers that are not perfect squares. And just to sort of get things started, in the case of radical equations, there is a property that's going to apply to even root radicals. And we have what's going to be regarded as the principal square root rule or property. And for what we have in the case of the principal square root rule, for the principal square root rule, this is going to state that the square root and while it is named the principal square root rule, we're looking at this rule to apply to even roots, period. So the square root or any even roots. And again, just for square roots, now if the index number happened to be displayed, it would be with the number 2. But again, you got square root or second root. You have the one and same entity, and for other even roots, you have like fourth roots, sixth roots, eighth roots, and so on. Now we have with the principal square root rule, we have the square roots or any even roots of an expression cannot reduce to a negative constant. And let me just mention, so the principal square root rule, this will apply to even roots. But again, the PSR, or short for principal square root, does not apply to odd roots. Odd roots like cubic roots, fifth roots, and so on. And just a bit of a backdrop. For what we have, just kind of going back to a quadratic equation we dealt with, like in the case of what was then solving by the square root property of equality. Like we had x squared is equal to 36. And when we went from x squared to x, we had plus or minus the square root of 36. And we had with the solutions, we had plus or minus 6. Again, we had with the solutions, again, we had negative and positive 6. And now we have with, the equation began with x to the second And with x to the second, okay, if like the equation is a conditional, like you have a limited number of solutions, you can have possibly up to 2 solutions, like depending upon the nature of the equation. It is in many but not all cases that the degree of the variable we are looking at solving for, the highest degree, will be indicative of the number of solutions there might end up being. Okay, now where we have radical equations to come in, and let's say that for x squared is equal to 36, you have negative and positive 6 for the solutions. But now let's say that where we can start out with radical equations. And if we're looking at solving for x, okay, and we'll say that if I had started out with, let's say x is equal to the square root of 36. Okay, now we have a conditional equation. Now we have for x, notice we don't have x to the second, okay, and the conditional applies to what we have here. And so think like x to the first equal to the square root of 36, and with the conditional, x is going to have one solution, and this is going to be the square root of 36, and the square root of a positive is going to be a positive only. So in this case, there is only one solution for this equation, and that is going to be at 6. Now, also in the mix, okay, where we can have, in the case of a radical, okay, if I have, again, like x is equal to the square root of 100, again, square root of 100 is going to be just one number, and that is going to be the positive value, and that's going to be at 10. Now, where we can have stressing the principal square root rule. Okay, if I have, let's say, the square root of x is equal to negative 4. Okay, and if you notice, okay, we have the principal square root rule, like you had the square root or any even root of an expression cannot reduce to a negative constant. And looking at what I have here, okay, we have the square root of x, and we're trying to reduce this to a negative constant, and because of the negative in front of the 4, there is no solution. Now on the other hand, if I had the square root of x is equal to 4, okay, now here 4 is non-negative, and we have the green light, okay, to proceed. Okay, so for the square root of x is equal to 4, and again I'm solving for x, and what I can do is I can take care of the x by removing the radical. And how can I remove the radical? Well, remember, with square roots the index number is 2, and to remove the index number and the whole radical, I can apply the matching exponential treatment. So in this case, we'll undo the square root by squaring both sides of the equation. So for the square root of x squared, okay, this will become x, and 4 squared is equal to 16, and the square root of 16 does check out as being equal to 4. All right. Now, let's say that if I have the square root of x plus 4 is equal to 7. Okay, so I'm looking at the square root of a binomial expression. Okay, so I got the square root of an expression trying to reduce to 7. 7 is non-negative, and so I can continue. So there's no violation of the principal square root rule. If I had -7 on the right, we could stop, saying there is no solution on the basis that the principal square root rule has been violated. Alright, so for what I have on the left, okay, so for the square root of x plus 4, this will go to x plus 4. We have 7 squared is 49. And if x plus 4 is equal to 49, okay, we're going to have the x is equal to 45. And let's say that just to kind of pair up here, if I have, let's say, the square root of 2x plus 5 is equal to -3. So I have an even root radical and trying to reduce the expression to a negative constant. Again, because of the negative sign, okay, we have no solution. Okay, now let's say if I were to modify the terms a bit. Okay, let's say if I had the cubic root of 2x plus 5 is equal to -3. Okay, now one might be tempted to say, well, I got a negative constant on the right, so there'd be no solution. But looking at the index number, okay, that is going to be 3. And again, we have with the principal square root rule, this does not apply to odd roots. And here we have a cubic root. So there's no violation of the principal square root rule since I'm dealing with an odd root radical. So what I can do here is that I can proceed, and this time I can take care of the cubic root. Again, you have the index number at 3, and I can apply exponents, taking both sides and raising to the third power. So we have 2x plus 5, and we have a -3 cubed. We got -3 times itself times itself. So this is going to be -27. So I have a two-step linear equation. And so just isolating the x term. Okay, so we'll have 2x is equal to -27 minus 5, which will be -32. And we have, upon dividing both sides by 2, okay, we'll have the x is equal to -16. And just kind of looking at what we have in the case of radical equations, okay, at the start. Okay, now these have, single appearance of x throughout. We're going to be looking at where x might appear more than one time, okay, in any of these radical equations. But I tell you what, just to kick things off, let's see what we get in the case of solving for x. And just for these items, okay, let's see what we get for x is equal to the square root of 400. Also, where we have the square root of 2x minus 4 is equal to 3. And see also the square root of x plus 2 is equal to -10. And we'll say also that we have let's say we have the fifth root of 3x plus 6 is equal to -1. Okay, so let's see what solutions, if any, we get for x out of these four problems. So just looking at what we have among these items, okay, we have for the first problem, we have that x is equal to the square root of 400. Okay, so there's going to be, okay, so we're going to have one value for x in this case, and with 400 as a perfect square value, okay, so the square root of 400 is going to come out to 20. Now for what we have in the case of the next item, okay, and here we have the square root of 2x minus 4, okay, is equal to 3. Okay, so you have an even root radical term set equal to a positive constant. So there's no violation of the principal square root rule. And so we can proceed by squaring both sides of the equation. Okay, so for what I have here, left-hand side becomes 2x minus 4. And we have 3 squared is equal to 9. Then we have with our two-step linear equation. Okay, so I can add 4 to both sides. And so we're going to have 2x is equal to 13. And we have upon division by 2, it can either write as a decimal at 6.5 or as the fraction 13/2. Okay, now for what we have in the case of the next item, okay, so we have the square root of x plus 2 is equal to -10. Okay, and this is going to be a very short answer item, because here we have a negative constant, and we're trying to get this to coexist with setting equal to an even root radical expression, and here we have already a violation of the principal square root rule. Okay, so in this case we have no solution. Now, for what we have in the fourth item, we have an odd root radical expression set equal to a negative. Again, no violation of the principal square root rule, since again the property does not apply to odd root radicals. And so I can take care of the fifth root by taking both sides and raising to the fifth power. So for what I have on the left, okay, we have 3x plus 6. And to the right, we have a negative to an odd power is going to be a negative. In this case, you have like -1. So you have alternating from negative to positive. And for -1, 5 of them multiplying each other out, or one another out, we have -1. And so we have in the follow through, we have for 3x plus 6 equal to -1. And we have taken 6 away from both sides. Okay, so we have that 3x is equal to -7. And we have with division by 3, we're going to have that x is equal to -7/3. Okay, so this will be like our first answer among the first non-negative integers that will apply for what we have seen among the radical equations. All right, so far we've had x to appear one time among the radical equations, and I'm about to expand the model and where we can have at least 2 appearances of x. Now let's say that if I venture out a little bit further and we look at solving for x, And let's say if we have x to appear twice, and we'll say that we have x is equal to 3 times, okay, the square root of x. Okay. If you notice, you have x to appear twice, one as the monomial itself, and x, right hand side we have 3 times the square root of x. If you notice, so far we've had throughout the examples, we've had the radical terms to be isolated. And for what you can technically do is that you can isolate the square root of x upon dividing 3. But if you don't care to work with fractions and just work with what we have, just keeping the coefficients, everything in direct fashion, what you can do is that you can go ahead and take care of the square root of x and just squaring both sides of this equation. And upon doing so, have x to the second is equal to 3 times the square root of x, also raised to the second. So for what I have to the left, okay, I have x squared. To the right, I have 3 squared is 9. Square root of x squared is x. Now we had the formation of a quadratic equation. So we have x squared is equal to 9x. And here, okay, now if I had x squared equal to 9, I could apply the square root property of equality. But since I have 9x as opposed to 9, we'll be looking at having to rewrite this quadratic equation in standard form. So setting equal to 0, okay, we have x squared minus 9x, and here we have with the difference of variable terms, we'll have a common factor with x, and x will go into x squared x times, and x will go into negative 9x minus 9. Now we have 2 distinct factors in x. Okay, one at x, and utilizing the zero product property. So we have x equal to 0, and we have x minus 9 is equal to 0, and if x minus 9 is equal to 0, I'm going to have that x is equal to 9. Now we have 2 apparent solutions with 0 and 9. And what I can do here is I can check the results. Now you don't have to write out the checking. If you can see visually, what we have, okay, just with the inputs. Okay, so again, we're working with x equal to 3 times, okay, the square root of x. And with x at 0, so 0 is equal to 3 times, okay, the square root of 0. Square root of 0 is going to be 0. And 3 times 0 is 0, and we got 0 equal to itself. Okay, so we have consistency, so 0 works. And as for the case of checking x is equal to 9, again, same equation, different input to test. Okay. So with x at 9, we have 9 is equal to 3 times, okay, the square root of 9. And the square root of 9 is going to be at 3. And 3 times 3 is 9, and 9 is equal to itself. Okay. So this particular radical equation, okay, just so happens we'll have 2 solutions in this one. Okay, so you have that x is equal to 0 as well as 9. Okay, so you have consistency throughout. Now they're going to be what are going to be regarded as extraneous values, and those, what I mean by extraneous is that you might have an apparent solution, but upon re-examining, it'll turn out that that particular value is not going to qualify as a solution. And we'll be looking into such a case in a moment. And let's say that if we have another situation where we have x to appear twice, and we'll say that we have that x is equal to 2 times the square root of x minus 1. Okay. All right, now in this one, okay, so I have x, I got 2 times the square root of x minus 1, and again, you can leave the radical expression as it is without having to perform any division. So I can remove the radical once again by squaring both sides. Okay, so for what we have here, squaring both sides, okay, so the square of x becomes x squared, and to the right, now 2 to the second is 4, square root of x minus 1, okay, that is going to be x minus 1, and let me pause for just a moment. Okay, so if I have a constant multiplied by an even root radical, like in the case where the radical is the square root, and I square that term, like 2 times the square root of x minus 1. Now if I square out, now 2 squared is 4, square root of x minus 1 squared is x minus 1. But the square of this expression is not going to be 4x minus 1. It's going to raise the coefficients and the terms. Like 2 goes to 4, square root of x minus 1 goes to x minus 1. But it does not undo the multiplication. So the square of this expression is going to be 4 times all of x minus 1. So in this case, we're going to have x squared is equal to 4x minus 4. And here we have a quadratic equation. And again, if I arrange the terms, whereupon I had the quadratic equation in standard form. So I got x squared on the left. I can just move the 4x and the 4 by respectively subtracting and adding. So we have in the rewrite, okay, so we're going to have x squared minus 4x plus 4 is equal to 0. And here we have a factorable trinomial expression. And again, for x squared, this will go to x and x. And factors of 4 that will add up to the middle coefficient, negative 4. They will be both at negative 2. And if you notice, we have a repeating factor with x minus 2. And we have with the zero product property, I need only one application of x minus 2 since x minus 2 repeats. And so we're going to have an apparent solution with x equal to 2. Right. And so just going back and checking. Again, you don't have to write out the checking. I just at least want to give a visual layout. Okay, so if I fill in, okay, so I got this equation, x is at 2. We have is equal to 2 times the square root, and x minus 1 is going to be 2 minus 1. And we have the square root of 2 minus 1 is going to be the square root of 1. And the square root of 1 is only 1. And 2 times 1 is 2. And we have that 2 is equal to 2. So we got consistency. And x equals 2 checks out. Okay, so if you have an even root radical, it is highly recommended that you double check. If you have like an odd root radical, like if I had like a cubic root of an expression equal to a constant, checking is not so much immediate, since you don't have like all those things like the principal square root rule to deal with. All right, now again, going back to the term extraneous, and this is a situation where we might have this to arise. Okay, now let's say if we have x is equal to the square root of 4x plus 12, right? Alright, so we have x on the left, and we have the square root of 4x plus 12 on the right. And the nature of the radical, again, being the square root, we can just go ahead and square both sides. Okay, so we have on the left, okay, we have x squared, and to the right, okay, squaring just leads to 4x plus 12. So we've got a quadratic equation. Again, so we're back to where we have x squared solely on the left, and you have your first degree and constant terms on the right. And again, we can join the first order and constant terms with x squared, again, by respectively subtracting and adding, okay, the x, a first degree term, and the constant. Okay, so we have in reestablishing in standard quadratic equation form, so we're going to have x squared minus 4x minus 12. Spoke a little bit too early. Okay, so you have x squared minus 4x minus 12, not plus 12. Is equal to 0. And here we have a factorable trinomial. Okay, so with x squared, we have x and x. Factors of negative 12 whose sum or difference will be on the minus side at 4. We have more weight given to the subtracting than to the adding. Okay, so we're in the terrain of where we can apply the zero product property. Okay, so for the first factor, if x plus 2 is equal to 0, we're going to have an apparent solution with x equal to negative 2. For what we have in the case of x minus 6, setting this equal to 0, we'll have that x is equal to 6. Now, looking at testing out the values. Okay, so I have negative 2. Now looking at what we have, just putting into x, again, the value of negative 2. Okay. All right, so with x at negative 2, so that negative 2 is equal to the square root of, what is going to be 4 times negative 2 plus 12. And 4 times negative 2 is negative 8. And negative 8 plus 12 is going to be 4. And so we got negative 2 on the left. Okay, now for the square root of 4, that's going to be a positive 2. So negative 2 is not going to test out. And negative 2 would be a case of what we have as an extraneous value. Okay, so there could have potentially been up to 2 solutions, but now we're going to have to look and see if we can have so much as 1 solution for this radical equation. Okay, so looking at 6 for x. You can see I have x at 6, and 4 times 6 plus 12 is 36, and the square root of 36 is equal to 6, and 6 is equal to 6. So that would check out. And so for this case, right, there's going to be 1 solution for this radical equation. Again, that is going to be at x is equal to 6. All right. Now, for what we have in the case of working with radicals, I'm going to give you some special cases in a moment. I'll tell you what, just for the next few moments, just a couple of items here. If we're looking at solving for x, just a couple of items here, and we'll be looking at other situations with radicals. And tell you what, let's see what we get for x is equal to 5 times the square root of x. And also, let's see what we get for x is equal to 3 times the square root of x minus 2. Let's see what solutions we get for x, if any. And we'll discuss in the next few minutes. Okay, for these items, okay, so in both equations, so I have x by itself on the left, and we have corresponding radical terms to the right. Okay, and again, I can free up the radicals. Okay, where we have nature of them, again, we have to be square roots. Okay, and so for both equations, I can take the square of both sides. And for what we have in the case of the first equation, okay, we have upon squaring both sides. Okay, so here I'm going from x to x squared, and for the square of 5 times the square root of x, okay, so this will become 25x. So I have x squared is equal to 25x, and if I rewrite this quadratic equation in standard form, so we have x squared minus 25x is equal to 0. And between the terms we have in the difference, we have x shared in common. And here we have x times the quantity of x minus 25 is equal to 0. And applying the zero product property. Okay, so we have an x by itself. Okay, we have already a first apparent solution with 0. And as for the other factor, x minus 25, setting this equal to 0, okay, so we have that x is equal to 25. Okay. And just taking what we have, So we have in checking x equal to 0. Right. So we have an x at 0, and 0 is equal to 5 times the square root of 0, and the square root of 0 is still 0, and 5 times 0 is equal to 0, and we do have that 0 is equal to itself. So 0 is going to check out. And to see if we have two solutions, this will write upon the consistency of x equal to 25. Okay. So here again we have x at 25. We have 5 times the square root of 25 on the right, and the square root of 25 is 5, and 5 times 5 is 25, and 25 is equal to itself. So we have consistency between both sides once again. And so we have two solutions with 0 and 25. Okay. Now for the next item, okay, we have upon squaring both sides. Okay, so again we're going from x to x squared, and to the right, now squaring the factors, so about 3 squared is 9, and that's going to be multiplying the square root of x minus 2. Right, so we squared the factors, but we still have distribution to perform. Okay, so we have x squared is equal to, and 9 times the quantity of x minus 2. Okay, this is going to be 9x minus 18. Again, we have x squared by itself, and across we have the first order x term and the constant. So if I move the 9x and the 18, we have for our quadratic equation, we have the trinomial x squared minus 9x plus 18 is equal to 0, and we have a trinomial that can be factored. Now for x squared we have x and x, and factors of 18, okay, that will add up to negative 9. Okay, so two numbers multiplying it to a positive will either be both positive or both negative. In this case you have both to be negative. One is going to be minus 3, and the other is minus 6. And setting the factors each to 0. So if I have x minus 3 is equal to 0, here we have that x is equal to 3. Upon setting x minus 6 to 0, we'll have the x is equal to 6. Again, we can check the results. Okay, so checking out x is equal to 3. Okay, so we have with x at 3, okay, so we have 3 is equal to 3 times, okay, the square root of 3 minus 2. And 3 minus 2 is 1. And the square root of 1 is 1. And 3 times 1 is 3. And 3 is equal to itself. So 3 is going to check out. As for x is equal to 6. Again, whenever you're checking, you don't have to write this out, but I'm just kind of showing you, kind of giving the concrete display. So you got 6 is equal to 3 times the square root of 6 minus 2. And the square root of 6 minus 2 is going to be the square root of 4. Square root of 4 is 2. And 3 times 2 is 6. And once again, we have upon examination, okay, both sides are equal. Okay, and so this equation likewise has 2 solutions with 3 and 6. Now, we're going to soon transition over to correspondence between radicals and non-integer exponents. Okay, but for right now, let me give you a special case of a radical equation where we have, now we've had 2x terms, and now let's say we have 2 radical terms in the same type root. I'll give you a case here. So for as an example of an equation with 2 radical terms, so we're looking at solving for x, and we'll say that we have the square root of x plus 5. Let's say we have minus the square root of x is equal to 1. Okay, so you have 2 distinct terms in the square root. Same type of radical with the square root, but here we have the square root of x plus 5 minus the square root of x is equal to 1. Okay, now we've looked at, like the radical terms being isolated. And for what we have here, but in the past recent past we've had 1 radical term. Now we got 2. And the common approach is to isolate what might appear to be the more complex radical. In other words, like that, it might have the higher coefficient alongside x, or that which might have more terms inside the radical. So between the square root of x plus 5 and that of x, okay, x plus 5, since we have 2 terms inside the radical, we can just isolate this term and move the square root of x over. And we have with this approach. So I'm going to have the square root of x plus 5 by itself. And have is equal to 1 plus the square root of x. Okay. And for any radical that is isolated, I can at least free up the inside expression once again by squaring both sides. Okay, so for the square root of x plus 5 squared, okay, so that's going to be x plus 5. Now, to the right, okay, so I have 1 plus the square root of x, quantity squared, and for the translation we have here, so you got 1 plus the square root of x squared. So this will mean 1 plus the square root of x times itself, okay, and if we FOIL out, okay, all right, okay, I'm just kind of stretching this on out, okay, so we have FOIL, almost like going back to day one, except we have radical involved, okay, so you got first part 1 times 1, we have 1 times the square root of x on the outside, inside, and the square root of x times 1. Now for the last, okay, you have the square root of x times itself. Now looking at what we have in the follow through. So 1 times 1 is 1. Outside product is going to be the square root of x. Inside product likewise. And the square root of x times itself. Okay, anytime you have the square roots and you have the term to repeat, it's just going to be what is inside the radical. So the square root of x times itself will be like the square root of x squared, which is going to go to x. And so for what we have in the follow through, so we've got 1, and we've got square root of x plus the square root of x. Think of this as like 1 square root of x plus 1 square root of x. And so we're going to have 2 times the square root of x plus x. And so going back to what we have with our equation. Okay. All right, so we've got x plus 5, we have is equal to 1 plus 2 times the square root of x plus x and if we combine, let's see, like terms, okay, and if you notice you still have a radical remnant, okay, with 2 times the square root of x. And say if I follow through just to isolate this term, so I can move the x as well as the 1. And if you notice, okay, we'll have x's to unanimously go out. And we have that 5 minus 1 is equal to 4. And we have that 4 is equal to 2 times the square root of x. Now for the follow through, you could either go ahead and square both sides, or you could isolate the square root of x by dividing by 2, where you still have 4 over 2 is going to be a whole number. If I had like 3 is equal to 2 square root of x, I would say go ahead and square both sides. But no one right way in this one. So here we have 4 over 2 is 2, and we have 2 is equal to the square root of x. And we have upon squaring both sides. Okay, so we're going to have an apparent solution with x is equal to 4. So just looking at what we have in the scheme of things. Okay, so And we have upon checking x is equal to 4. So going back, okay, so I have square root of x plus 5, we have the square root of 4 plus 5. And minus the square root of x, so this will be minus the square root of 4. Is equal to 1. 4 plus 5 is 9. And for the difference, square root of 9 is 3. Square root of 4 is 2. And 3 minus 2 is 1. And 1 is equal to itself. And so it's going to follow that 4 is going to check out for this equation. Okay, and so we do have the unique value at 4 for this difference of radicals. And to tell you what, is for an equation with 2 radicals. So, let's see what we get in the case of let me do this. Let me change that. Yeah, we'll go with this one. Okay, let's see what we get for x whenever we have the square root of x plus 6 plus the square root of x plus 1. So we're going to have this time the sum of radicals where we have is equal to 4. So let's see what we get for x if there is any solution. Okay, for this radical equation, here we have the square root of x plus 6 plus the square root of x plus 1 is equal to 4. And I tell you what, just for this thing, it just happened to hit me. If I can do my math right. We'll say it's equal to 5. Sorry about that. All right. Okay, square root of x plus 6 plus the square root of x plus 1 is equal to 5. Okay, now for working with sums and differences of radical terms, now the details involved can get rather granular. Okay, so if I have the square root of x plus 6 plus the square root of x plus 1 is equal to 5, not 4 but 5. All right, so we have 2 radical terms with the square root of x plus 6 and the square root of x plus 1, and you can isolate either of the radical terms. And we'll go ahead and isolate the square root of x plus 6. And we have in the rewrite, okay, so we'll have the square root of x plus 6 is equal to 5 minus the square root of x plus 1. And looking at with the square root of x plus 6 isolated, I can free up x plus 6 upon squaring both sides. Okay, so for the square root of x plus 6 squared, okay, so this will go to x plus 6. Now, for what I have in the case of 5 minus the square root of x plus 1 quantity squared. Okay, so this would translate to 5 minus the square root of x plus 1 times itself. And just looking at the breakdown in terms of the FOIL method. Okay, so first product have 5 times 5. Okay, so this would be 25. Outside products, we will have 5 times the negative of the square root of x plus 1. So we have minus 5 square root of x plus 1. Inside product, we will have another negative 5 square root of x plus 1. Okay, now last part we have a negative times a negative. Okay, so that's going to be a positive. And the square root of x plus 1 times itself will give you x plus 1. Okay, so again, have the FOIL first, outer, inner, and last. Okay. Again, so you have 25. Now for the outside, the inside products. Now both of these are square root of x plus 1 terms. And combining coefficients. So this will come out to negative 10 times the square root of x plus 1. Again, last product we have x and 1. And I have constants with 25 and 1 that I can join. Okay, so we got 25 plus 1, that'll be 26. I have minus 10 times the square root of x plus 1. And again, half plus x. Okay, so just relaying back. Okay. Okay, so we have x plus 6 is equal to 26 minus 10 times the square root of x plus 1 followed by the addition of x, and for what we have and following through. Okay, and so just notice we have still a radical term with negative 10 times, okay, the square root of x plus 1, and just moving the x and the 26 over. Okay, so if I deduct x, you notice we have complete cancellation of the first order x terms, and for 26, if I deduct, and we're going to have 6 minus 26. Okay, so this will become negative 20. We have is equal to negative 10 times the square root of x plus 1. And what I can do here is I can isolate the square root of x plus 1. So dividing by negative 10. Okay, so left-hand side is going to become 2, and we have is equal to the square root of x plus 1, and one more round of squaring to perform. Okay, so 2 squared is 4. And we've got 4 is equal to x plus 1. And if you take 1 away from 4 and isolate x, we're going to have an apparent solution with 3. And I'll tell you what, if we just kind of look at plugging in, okay, so if x is at 3, 3 plus 6 is 9, square root of 9 is 3, 3 plus 1 is 4, square root of 4 is 2, and 3 plus 2 is equal to 5. So x equals 3 is going to check out, and so this radical equation is also going to have, once again, one solution, and that is going to be with the value of 3. Okay. Now, crossing over, and again, radical equations, especially those with two radical terms, yeah, those can get pretty strenuous. Again, with the small details that are often incurred. Now, again, I had mentioned that we would have correspondence between radicals and non-integer exponents, and we have in crossing over, and we have in the case of equations with non-integer exponents. Okay, just some of the properties we have, okay, like corresponding radicals and non-integer exponents. Okay. So you have an exponential base a, and we have to the fractional power, we have m over n. If I write this as a radical, again, if I have a non-integer exponent, it could be an integer, but we'll say the m over n is a non-integer. Now the denominator, the fraction, that's going to define the type of radical we have. So the denominator in the non-integer power is going to be the index number of the radical. So a to the m over n, that is going to be defined as being the nth root of a to the m. And just some examples here, like if I have an expression such as x to the 2/3. Okay, so your denominator value is 3, and that is going to be the index of the radical to which that term is going to be translated to. Okay, so we'll end up with a cubic root of x squared. And if I have, let's say, an expression, if I have, let's say, b to the 3/2. Okay, so the denominator we have at 2, and so we have the index number is going to be at 2, so we're looking at the second root of b to the 3rd, and again, second root radicals, those are just going to be square roots. So b to the 3/2 is going to be the square root of b to the 3rd. And if we have, let's say, y to the 2/5, again, 5 is the denominator, so this would be the 5th root of y squared. And say if you have another case of an example of where we can have a to the m over n, and we'll say that we have, so we have for z to the 4/3. Again, so we have with the 3, so we have another cubic root expression, and so that'll be the cubic root of z to the 4th. So for equations with non-integer exponents, okay, you're going to be looking at translating between the non-integer exponential expressions to their radical equivalents. Okay, say if we have crossing over, and I'm just going to put up a couple of cases here. And go on to the next item. So we'll touch upon this rather lightly, but we're going to get back to it. And let's say we have an equation with a non-integer exponent, and you're looking at solving for x, and we'll say that we have x to the 3/2 is equal to 8. In fact, I think I'll put in an additional case, but we'll get to that in just a moment. So you got x to the 3/2 is equal to 8. So if I write x to the 3 halves in terms of a radical. So you got second root of x cubed is equal to 8. Again, second roots, you have the square root of x cubed is equal to 8. Alright, so you got the square root of an expression equal to 8. 8 is non-negative. And what I can do here is I can free up x to the third from the radical. So if I look at squaring both sides, okay, so the square root of x cubed, we have raised to the second, again the radical and the exponent will cancel out. So x cubed is going to be freed up, and we have our 8 squared. 8 squared is going to be 64. Okay, so we're at the stage where we have x to the third is freed up, and it is set equal to 64. Now if you notice, I just use exponents to eliminate radicals. And guess what? I'm looking at solving for x as opposed to just x cubed. So I'm going to be shifting gears. Okay, and so instead of using exponents to cancel out radicals, I'm going to be going in the other direction. And that which is going to cancel out x to the third is going to be taking the cubic root. And if I take the cubic root of both sides, and the cubic root of x cubed, okay, that is going to go to x. And for the cubic root of 64, it'll be that number times itself will give you 64. And 64 is one of those special numbers that is simultaneously a perfect square and a perfect cube. Like 64 is going to be the square of 8, but also 64 is going to be the cube of the number 4. Okay, and so in this case we have the x is equal to 4. And if you were to test this out with your calculator, so if you were to try to enter, I can have like 4 to the 3 halves. If you enter a fractional exponent for many models, okay, you want to put the exponent in parentheses, and so 4 to the 3 halves, and the outcome should be at 8. 4 raised to the 3 halves power is equal to 8. And if I have, say, another situation, and if I have like x to the 3 halves is equal to negative 27. Again, if I translate from non-integer exponent to radical, so again we have a square root, this will be of x cubed is equal to negative 27. And guess what? Again, for the principal square root rule, the square root or even roots of any expression cannot reduce to a negative constant. Again, the basis for no solution again is your principal square root rule. And one more case of what we have with non-integer exponents. If I have, say, x to the 2/3 is equal to 9. Okay, now this is going to be a case, and there are some equations with non-integer exponents where many calculators, even some mathematical programs, okay, will not have all the solutions on display. And for x to the 2/3 equal to 9, okay, now for x to the 2/3 equal to 9, if I translate, okay, from non-integer exponent to a radical, okay, so this is going to be this time the cubic root of x squared is equal to 9. Okay, so here, okay, the principal square root rule doesn't apply directly here, and so because we have an odd root radical. Now I want to free up the x squared from the radical. In this case, we'll have the cubic root and so we get rid of the radical by cubing both sides. And I know there's some problems where, working with non-integer exponents, it can get, especially when you got exponents and radicals and then application of additional radicals or exponents, it can get to be probably more work for the eyes than even just testing your math skills, so to speak. And for the cubic root of x squared raised to the third, so we have x squared and 9 to the third. We have 9 times 9 times 9. So this will be 729. Okay, so we got x squared is equal to 729. Okay, and so we're back to where we can utilize the square root property of equality. Again, if you have like x squared is equal to p, x is equal to plus or minus, okay, the square root of p. And so with p at 729, we're going to have that x is equal to plus or minus the square root of 729. And like 64, 729 is both a perfect cube and a perfect square. And while the cubic root of 729 is 9, its square root is going to be a larger value, in the case of 27. And it's going to turn out that for this equation, we'll have two solutions for x, and there will be additive inverses. So one we have at 27, the other we have minus 27. And there are some calculators that will probably not pick up the negative solution, but for what you have in essence, so with negative and positive 27, again, if you're looking at trying to test out, see what the capabilities of your calculator are, again, anytime you have a negative value to raise to a power, do not forget to put in parentheses for many of the models. And negative 27 raised to the 2/3, that should be equal to 9. And likewise with 27, I just mentioned this. Let's kind of string this out a little bit further. Yeah, just some of the syntax here. Okay, so you got negative 27. And anytime again that you use fractional exponents, you might want to include parentheses. So you have negative 27 to the 2/3. Okay, that is going to be equal to 9. And for 27 to the 2/3, we have 27 to the 2/3. Okay, that is also equal to 9. All right, and we'll get back to equations with non-integer exponents. Okay, but just one more situation, and just sort of transitioning away from the radicals at the moment, and we have for the next portion, okay, in the chapter, and this is going to be what we have in the case of absolute value. And for absolute value equations, okay, just some of the notation here. Okay, for absolute value, okay, so you have the absolute value of x is going to be written as like x inside vertical bars. Okay. And by definition, okay, so we have for absolute value of x, for the absolute value of x, okay, that is going to be the number of integral steps number of integral steps x is away from 0 on a number line. And just looking at numerical cases. Right, so we got say for the absolute value of 14. Okay, well 14 is going to be 14 steps away from 0. And if I have, say, the absolute value of negative 37, well, negative 37 is going to be, say, 37 units to the left or behind 0. So the absolute value of negative 37 is going to be like 37 integral steps away from 0. And if I have the absolute value of 0, well, there's no movement away from 0, so you're going to have 0. And just to mention, okay, so you have absolute value is a non-negative quantity. It can be 0 or positive, but never negative. And for what we have in the crossover to absolute value equations, say that if k is a non-negative value, and we have that the absolute value of x is equal to k, then the possibilities that will exist for x is that you're going to have x could be k or negative k. Now let's say that in terms of what we have in absolute value equations, just to kind of get things started. if we're looking at solving for x, let me see, we have in the first case, right? So we'll just say we have just a standalone term. Let's say we have the absolute value of x is equal to 7. Okay, so we got absolute value is equal to k. Here k is at 7, and 7 is non-negative in value. Okay, and so here, okay, so we're looking at the values of x whose absolute value will be 7. Okay, so there are two numbers that will be 7 units away from 0. One is going to be 7 at the upper end, and the other value will be at the lower end where we have negative 7. And so we have for the solution set here, we have x equal to negative as well as positive 7. Absolute value of negative 7 is 7. Absolute value of 7 is equal to 7 itself. Now, let's say if we kind of change things up a bit, and let's say if we expand the model, instead of having just a standalone absolute value of x, let's say if I had the absolute value of 2x minus 7 followed by the addition of 2 is equal to 19. Okay, so I got the absolute value of 2x minus 7 followed by the addition of 2 is equal to 19. Okay, so what I want to do here, first of all, okay, I want to isolate the absolute value term. So upon isolating, so I can move the 2 over. Okay, so left hand side we have just the absolute value of 2x minus 7. And to the right, okay, so I have 19 minus 2 is going to be 17. So right now, okay, the k value is going to be 17. 17 is non-negative. Absolute value of x is represented by the absolute value of 2x minus 7. Okay, and now at this stage, going from the absolute value of x equal to k to x equal to the plus or minus k stage, I can take out the absolute value bars surrounding 2x minus 7. And have 2x minus 7 equal to plus or minus 17. Okay, so we have two modes of operation for 2x minus 7. One is going to be setting the binomial to negative 17 as one possibility in the lead up to x, and the other one we have, in this case, we have 2x minus 7 is equal to 17. So we have at the lower end. Okay, so if I isolate the x term, and we have upon adding 7, okay, so I have 2x is equal to negative 17 plus 7, so this would be negative 10. And we have with division by 2, okay, so we're going to have the x is equal to negative 5. Now, for what we have with 2x minus 7 equal to 17, so if I isolate the 2x once again, and we have upon adding 7 in this equation, we have 2x is equal to 24, and with division by 2 we have that x is equal to 12. Okay, so there'll be two values of x that will ring true in this absolute value equation. So we have one value we have at negative 5, the other at 12. Now, let's say that for what we have, say it's a third case. I'll say that I have the absolute value of x will be represented by the absolute value of x plus 5 is equal to negative 16. All right, so some things here. Okay, so to be able to work with an absolute value equation. Okay, so again we have for k. Okay, so k is going to be a non-negative value. Okay, and so for non-negative, anytime you have the absolute value term isolated and the constant on the other side is negative, it's going to mean that for what we have for this absolute value equation, okay, there's going to be no solution. All right, now another case here, okay, and this remaining example now we have with the absolute value bars in terms of how they are to be applied or looked at. So just kind of bring up, let's say if I have negative 3 times the absolute value of 2x plus 6 followed by the addition of 6 is equal to negative 24. Okay, now for this setup, notice we have in front of the absolute value bars containing 2x plus 6. We have negative 3 at the front. Now I could see why, but there might be the tendency to try to distribute negative 3 over 2x plus 6. The thing about this, in this particular example, do not treat the absolute value of 2x plus 6 as you would if you had 2x plus 6 in parentheses. So in negative 3, there's not going to be any distributing. So what you have to do, okay, is isolate the absolute value of 2x plus 6 and have everything else on the other side. Okay, so we have with this absolute value equation, it would be nice if you could distribute, but here I have to isolate the absolute value of 2x plus 6. Okay, so we have with this equation, okay, I can start out, say, like meaning a two-step linear equation, or in this case where I have an absolute value equation. I can undo the addition or multiplication here. I'm going to subtract 6 from both sides. So right now that's going to leave us with negative 3 times the absolute value of 2x plus 6 is equal to, and negative 24 minus 6, this is going to be negative 30. And to get the absolute value of 2x plus 6 by itself, so I'm going to divide by negative 3. So we have the negative 3's to go out. So this will bring us to the absolute value of 2x plus 6 is equal to 10. Okay, so right now at this juncture, okay, we had the absolute value of x to be represented by the absolute value 2x plus 6, and here we have k to be represented by 10. Okay, so 10 is a non-negative value. So going from the absolute value of x is equal to k to the stage of x is equal to plus or minus k, we have upon removing the absolute value of bars, we have that 2x plus 6 is going to go in either of two directions. One where we have equal to 10 and the other negative 10. And looking at setting up our linear equations simultaneously. So we have, again, one way that 2x plus 6 will go will be when it is equal to negative 10. And the other way will be whereupon we have 2x plus 6 is equal to 10. And just looking at what we have in the follow through. Okay, so in both equations, if I take 6 away from both sides, so we have that 2x is equal to negative 10 minus 6, so we have negative 16. Okay, so one solution is going to land at negative 8. For 2x plus 6 equal to 10. Again, if I subtract 6 from both sides, we have 2x is equal to 4, and we have a division by 2. Then we have the x is equal to 2, and so we have two solutions for x in this absolute value equation. So we have on the minus side we have negative 8, and on the plus side we have positive 2. And then just for what we have for absolute value equations, and for what we have in these items, so let's see what we get. First of all, say we have the absolute value of x is equal to 15. Then we say we have the absolute value of 2x is equal to 22. And we'll say we have in the remaining case, okay, we'll say that we have negative 4 times the absolute value of 2x minus 2 plus 10 is equal to negative 54. Okay, with these absolute value equations, okay, first two items, especially the first case, is going to be a short answer. And for the absolute value of x is equal to 15, so you have k is represented by 15. 15 is non-negative, so we will have at least a solution for x. Okay, so for the absolute value of x equal to 15, okay, we have the value of x will be, or the values of x will be those numbers that are 15 units away from 0. And so we'll have that x is going to be positive or negative 15. So two numbers with absolute value of 15. We end up with 15 as well as minus 15. For what we have in the second item, okay, so we had the absolute value not of x but of 2x is equal to 22. And okay, so again I had the representation of the absolute value of x by itself with the absolute value of 2x. And if I remove 2x from the absolute value symbolism, and we have with the k value at 22, and we have that 2x is equal to plus or minus 22. And so we have at the one end, we have that 2x is equal to negative 22. At the other end, I have 2x is equal to positive 22. And if 2x is equal to negative 22, I'll have that x is equal to negative 11. And with 2x equal to 22, we'll have that x is equal to 11. So we have our solution values in x to be positive and negative 11. And in a sense, you can go back and check. 2 times negative 11 is negative 22. And the absolute value of negative 22 is 22. 2 times 11 is 22. Absolute value still at 22. All right. Now, for what we have in the last of these equations, okay, so we got negative 4 times the absolute value of 2x minus 2 followed by the addition of 10 is equal to negative 54. And taking what we have here, okay, again, we do not treat the absolute value of 2x minus 2 grouping as you would parentheses. So again, we'll isolate the absolute value of 2x minus 2 and working around it. And I can proceed by taking 10 away from both sides. So here we're going to have negative 4 times the absolute value of 2x minus 2 is equal to, and negative 54 and negative 10 will become negative 64 and getting the absolute value of 2x minus 2 by itself. Okay, so if we look at division by negative 4, so this will come down to the absolute value of 2x minus 2 is equal to 16. And again, just removing the absolute value bars. Okay, so this will come down to 2x minus 2 is equal to plus or minus 16. And setting up this equations. Okay. So for 2x minus 2 is equal to negative 16. And both as well as equal to positive 16. So if I add 2 to both sides in both equations. Okay. So for left hand side we have 2x. And where we have negative 16 plus 2, that will be negative 14. And for 2x equal to negative 14, then we'll have the x is equal to negative 7. As for 2x minus 2 equal to 16, adding 2, we'll have that 2x is equal to, adding 2, we'll have that 2x is equal to 18. And dividing by 2 will come out to x is equal to 9. Okay, and so we'll have a couple of solutions here in this absolute value equation. And so we have on the minus side we have that x is equal to negative 7, and on the plus side we have that x is equal to 9.